All right, let's go ahead and get started. So before we get into the new stuff, just want to remind you again that we have a test coming up on Wednesday evening. So that's Wednesday, is that the 16th? Yep, 16th. So we're going to do the same thing as last time. Basically, the first hour and a half of that period will be just basically open review. So I'll be here. Really, I'll be in this room starting at 5:30 for office hours. But really from 5:30 to 7:40, you can show up, ask me whatever questions you want. We can work through examples, basically whatever you need to polish up on. But yeah, for the last test, I basically had a lot of people there, for 2 solid hours asking me questions. I think that was really good. So don't have to show up to the review if you don't want to, if you feel like you're just ready to go for that test. But yeah, if you have anything at all that you need to practice and polish up on, I would really recommend you be there. But yeah, that's again, that's Wednesday, June 16th. And that's our second and final quote unquote midterm exam before the final exam on the 24th. Yep, the 24th. If you haven't noticed, and I just put it in maybe 3 or 4 hours ago, there's a new module on Canvas which is called Exam 2 Prep Materials. Right now, the only thing that's in there is there's a file that is full of some good sample problems from all the sections we've looked at that are going to be on that test from chapters 8 and chapter 8 and chapter 11, and including the 3 that we're going to go over tonight. So take a look at those. Some good additional practice. Other things I recommend you take a look at are basically all the old homeworks and quizzes from this unit, and not only the quizzes, but I'm not sure how many of you open up the quiz solutions that I post. If you're having really any trouble at all, or just kind of maybe you understand the way you did it and the way you did it is perfect, but maybe just to take a look at another approach you can take. So yeah, please consult those quiz solutions. I try to make those as complete as possible. But yeah, if you need any clarity on those, or if you need anything explained at all, please send me an email, come to office hours, stick around after class and ask me questions. Yeah, anything I can do to help you get ready for next Wednesday, please let me know. So let's go ahead and get into the new stuff here. So the last thing we talked about last night was power series and how to analyze them. Now we're going to go a step further and represent functions as power series. So let's go ahead and get started. So this thing we've looked at a few times, but it's a good way to get started. So we've looked at this series before. Hopefully we can see the pattern now. So this is a power series, but what other kind of series can we characterize this as? How else have we classified it?
Geometric?
Yeah, it's a geometric series. And we know that the sum of a geometric series is basically equal to this, A over 1 minus R, where A is the first term and R is the common ratio of the series. So in this case, what we have is first term is equal to 1 and common ratio is equal to x. So from there, we know that this sum is equal to, so this infinite sum, which really is what the function is is 1 over 1 minus x. So for the first half of tonight, maybe even longer, we're going to see a lot of different ways to take functions and represent them as power series. But right now, our only real weapon is going to be, we want to represent functions as a power series, and really by drawing a parallel to a geometric series. A geometric series is just to kind of look back. We have lots of good methods now for determining if a series converges or diverges, but for the convergent ones, we don't really have a good means to find the sums. And the geometric series are kind of one of the two exceptions we've talked about. We know how to find the sum of a geometric series when it exists. So because we can think of this series as a geometric series, we can pretty easily find that sum. So hopefully this looks familiar. We've done this a couple of times. Now we're kind of building up on it. So now I want to find, let's go the other way. So I'm giving you a function here. Oh, go back. And I'll go ahead and write up here. Really, like I said, our only weapon so far is to try to represent these functions as the sum of geometric series. So that's 1 minus r, isn't it? Yeah. So basically, I would like to do the same thing here with this function. So can I take this function here, and can I represent this as a geometric series? And if so, what are the values for a and r? Let's start with a. A is probably a little easier to see. What's our first term going to be here?
1.
Going to be 1. The common ratio is maybe a little harder to pick out. So if we try to, look at the way our infinite series, our infinite sum formula stacks up with this, some of you have probably noticed that the formula I have here has a negative sign, 1 minus r, but this one doesn't. The function we're trying to actually deal with does not. So I'm going to rewrite this as 1 minus negative x squared. So now that we have that, let's start representing this as a power series. We know that we have a geometric series if we make these manipulations. I know that my first term is going to be 1. What should my second term be?
Would it be negative x squared?
Yep, negative x squared. And then the next term would be if I multiply negative x squared by the previous term, so I get positive x to the 4th minus x to the 6th plus x to the 8th, and so on. That really should be a negative sign. So if I do that, in order for me to generalize this, or in order for me to figure out what the interval convergence is, I really need to generalize this. So what's the pattern that's going on here? Or what are the patterns? What behaviors do I see from one term to the next here that will help me basically write my, my formula for my nth term in this sequence?
It's alternating.
So it's alternating. So let's put in this alternating term. How about negative 1 to the n? So I know I'm alternating, but if I do -1 to the n, n starts at 0. So that'll make my first term positive, second term negative, third term positive. So that alternation's good. What else do I need to add to this?
Would it just be x squared?
So
Or
x squared. So be careful. I mean, you're very, very close, but if I put an x squared in here, then really all of my terms are going to have x squared.
would
So
x to the 2n?
x to the 2n, really, that's what I want. I don't want x squared. I want to have my powers on x increase by 2 every time. So this is my power series. So if that infinite sum is going to give me this function 1 over 1 plus x squared. From there, I want to find the interval of convergence. So what tool do I need to use to help me figure that out?
Ratio test?
Yeah, it's a ratio test. So if I use the ratio test, I'm looking at this limit. So I have -1 to the n plus 1 times x to the 2 n plus 1. So the -1 terms here, all I'm going to be left with is a -1 to the first power in the numerator. So I'll cancel like this. From there, I should probably be a little more careful with the x terms. So I have x to the 2n plus 2 over x to the 2n. And then if I apply the absolute value, well, the absolute value is going to make the -1 irrelevant. But really what I have is this. So I have the absolute value of x squared is less than 1. But since actually I'll just go ahead and leave it like this. From here I can take the square root of both sides and then I'll end up getting the interval or the radius of convergence. So here is my radius convergence is just equal to 1. So basically anything that's less than 1 unit away from 0 is going to give me a convergent series. But now remember, what do I have to do to, I got the radius, but now what do I have to do to find the interval convergence? I have to look at both the endpoints. So I got x equals -1. I'll go ahead and test that. So I get -1 to the n times -1 to the 2n. The -1 to the 2n there, that is going to be the same as this. If I split it up like that, hopefully you see that -1 squared is just going to make that always equal to 1. So then what I have is this series. And let's go ahead and bring it back to some older stuff here. Does this series converge or diverge?
I don't know.
So,
Diverges, right?
sorry, what was that?
Does it diverge?
It diverges. So one thing I want to bring up, just because it's been a while since we've really talked about it at length. Look at what our
I mean-
sequence is here.
Professor, like, what does it raise to? It's just -1. How do you?
It's
how do
just
you-
-1.
How-
Because, so if you're okay with the way I split it up here as -1 times negative, oh, you know what? I messed up. Yeah, that should have been -1 the whole time. -1 to the end. So yeah, this diverges. We've talked about this alternating series. That diverges. So what happens if I do x equals 1? So -1 to the n times 1 to the 2n. So I'm going to have the same series. So that diverges as well. So our interval of convergence was complete when we first got it. Between -1 and 1, and I could not include either endpoint. Any questions there? All right, let's go ahead and look at another one. So I have 1 over x plus 2. So, you know, our whole mission here is to make these look like infinite geometric sums. So we'll go ahead and start with that. And just to more closely mimic what we are trying to get to, I'm going to rewrite it as 1 over 2 plus x. So there's one pretty crucial difference, or one very important difference between what I have written for f of x and what I'm trying to mirror, this a over 1 minus r. Does anybody see what that subtle but very important difference is?
The negative sign?
The negative sign, yes, that's part of it. So you're going to have to deal with that. What else?
Also, the 2 needs to be a 1.
Yeah, so in order to get to this, to help us, follow this, this geometric series path, we really need to have that first term, the constant term in the denominator, be 1. So I'm going to go ahead and rewrite this as 1/2 times 1 over 1 plus 1/2 x. And like someone said, we need to have a negative sign, so I'll go ahead and make that change as well. 1 over 1 minus -1/2 x. So from here, if there are any questions about how I got here, go ahead and ask me. But yeah, now that we have this form, now I can represent this function as an infinite geometric series. So I still have 1 in the numerator, so that's my first term. So a equals 1, and my common ratio is going to be -1/2 x this time. So 1 minus 1 -1/2 x plus 1/4 x squared minus 1/8 x cubed plus 1/16 x to the 4th, and we'll go ahead and stop there. And now that I have this, I'm going to go ahead and distribute this half. So 1/2 minus 1/4 x plus 1/8 x squared So now that I have this, my geometric series in a good form here, I would really like to make this look like or try to find up some formula to help me here. So hopefully we see that the alternation is here again. So I have to have that -1 to the n. What else do I see? Hopefully we see the x to the n. And I also see that my denominator is doubling each term. So I'll go ahead and put in 2 to the power of n. So we see that it's doubling, but let's test out a few things here. When n equals 0, I'm going to have 1 times 1 over 2 to the 0, so that'll be 1. So that doesn't quite work. So I really want my first term to have 2 in the denominator. I want my second term to have 4. I want it to double, but I need this ratio to be, or I need this power to be 2 to the n plus 1. And I will go ahead and pause there to make sure that people are okay with how I got that. All right, so from here, I got my power series, so let's go ahead and use the ratio test to find that interval of convergence, or at least to start finding it. So let's look at this limit. So from here, I'll go ahead and start. We've been doing a few of these. I'll go ahead and start canceling things a little quicker. But luckily, a lot of this gets simplified. And since we have absolute value, I'm going to go ahead and I'm going to start ignoring the alternation, because that just boils down to +1. So ignoring the alternation, that's going to go away. I'm going to be left with, in the numerator, x, and in the denominator, I'm going to have 2. And I want to have that. That's going to give me absolute value of x over 2 is less than 1. But if I solve for the absolute value of x, I'm going to get this. Absolute value of x is less than 2. So here is basically, I know everything inside this open interval is going to converge. So I have my radius of convergence is equal to 2. So that's good to see. But then what happens at the endpoint? So when x equals -2, I get this series.
There's one in the small garage, how to use the far end of the garage, the big garage.
So now I have a constant sequence, and I'm trying to take a series with it. So this is the question I was trying to ask last time. It didn't really work out. This sequence, 1/2, does that sequence converge or diverge?
That would diverge. Or the sequence,
The sequence, yes.
that would converge.
The sequence converges, but the series diverges because the sequence does not converge to 0. So this one right here diverges. So what happens when x equals 2?
Where's Izzy going? Izzy? Izzy's trying to say bye. What are you doing, Grandma? Bye, Sarah. Bye. I'll see you in a few days. Bye.
Oh, sorry, let's go back. So from there, hopefully we can see that this alternating series is just going to divert, or it's just going to, the sequence is going to go between, oscillate between -1/2 and +1/2. So this one diverges as well. So I just get the interval of -2 to 2, both ends open. Any questions on this one? All right, so this next one here. So here's the sum I want. So how is this function, x cubed over x plus 2, how is this related to the one we just did?
Has the same denominator.
Same denominator. So really all that's different is the numerator. So we'll go ahead and get started. But from here, I'm going to have, I know that I need to make these manipulations same as last time.
Oh, she wants to. That's not lock the door. That's not lock the door. Okay, bye.
But hopefully here you see that I have still the same common ratio of -x/2. But what has changed is my x cubed. So from there, what I really have is factor out the 1/2, which I already did. First term is going to be x cubed. Then the next term is going to be -x/2, or yeah, -x/2 times that, so -1/2 x to the 4th plus 1/4 x to the 5th. But really from here, actually maybe we'll keep going. So we'll go ahead and distribute now. So let's start building this this power series. So again, I'm going to have the alternation. again, I'm going to have 2 to the n plus 1 in the denominator. But if we compare this to the last one we just looked at, I know that when n equals 0, x is going to be equal to 3. When n equals 1, x is going to be equal to 4, and so on. So instead of having x to the power of n, what I'm really going to have is x to the power of n plus 3. So any questions on how I got this power series definition? So let's start looking at the ratio test again, so you can figure out that interval. So from here, hopefully this looks familiar. If we go back up a slide and we look at this step here, really everything from here is going to follow the same. Basically, we're going to reach all the same conclusions. So because of that, I can kind of fast forward to the end and say that my interval of convergence is from -2 to 2, excluding both endpoints. And if you think about it, that should make sense that our conclusion is the same, because if you have a geometric series that converges, basically multiplying all the terms by some constant is not going to, it'll converge to something else, but it will still converge for all the same conditions. It'll still converge when the ratio is on the same interval. So any questions with that one, or especially how I kind of fast forwarded to that conclusion at the end? All right, let's keep on going. So now that we can represent these functions as power series and vice versa, we can do differentiation integration with them. So one theorem to give you here is that, so we know that a power series has a radius convergence, unless except in the case where it only converges at one point, you're going to have some radius convergence. Could be some positive whole or some positive finite number. It could be infinity, where when it converges everywhere. But let's suppose that we have a power series that has a radius convergence. Then basically that power series is going to be differentiable everywhere on that radius, on the open radius. So if I have a power series, I can definitely take a derivative of it on its interval, or within its radius of convergence. So one thing I want to point out here, subtle difference here, there's a difference between the radius of convergence and the interval of convergence. And maybe I should ask you all, what is the difference between these two things? Or another way to phrase this, what does the interval of convergence tell us that the radius does not?
I know that the interval of convergence tells us where all the x values that converge,
Right.
but radius just tells you where the x values are being plugged in, maybe?
You're close, and I think I'm probably not phrasing this as well as I need to. Well, let's go back and I'll give you something more concrete. And in fact, it's a little hard to think about since we haven't come to an example yet today where they're different, but let's go back to this step here, this limit as n approaches infinity of x over 2. That right here tells me that everything strictly between -2 and 2, all those x values are going to give me convergence. So from here, yeah, I know that anything within 2 units of of 0 is going to give me convergence. But what the interval convergence tells us that the radius will not is basically what's happening at the endpoints. So what's happening when x is equal to a minus r, or when x is equal to a plus r? So for the radius, if I know what the radius is, I know everything that's like strictly inside that radius is going to converge. But I still need to look at the endpoints. So what I want to do here is I just have a generic power series. And what I want to do is find a derivative. So what I'm going to do first here is let's just write out the first few terms in this series. And I don't know if I've talked about this before, but basically this C sub n, this is just a list of constants. These are a list of coefficients for this series, which we don't necessarily need to know what they are, but it's just a list of constants. So first term, I'm going to have that coefficient C0. And then when n is equal to 0, then the x minus a is just going to, that's just going to, when it's raised to the power of 0, it's going to be 1. Next term is going to be C sub 1 times x minus a. Then C sub 2 times x minus a squared plus C sub 3 times x minus a to the third plus C sub 4 times x minus a to the fourth. So on. So remember, power series, except for the fact that it never ends, it looks exactly like a polynomial. This looks just like a polynomial. So that means I should be able to take a derivative of this, term by term, the way I'm used to. So having this, what's my derivative equal to? Let's just go do it term by term. What's going to happen to that C sub 0?
It's just gonna be 0.
Yeah, first term is just going to be 0. Second term, first derivative of x here is going to be 1. So this is just going to be plus C1. Actually, I'll go ahead and put some more details in here. Times x minus a to the 0. And plus 2C2 times x minus a to the 1. Plus 3C3 times x minus a squared. plus 4c4 times x minus 8 the third. So simplifying this a bit, I'm going to have c1 plus 2c2 x minus a plus 3c3 x minus a squared plus 4c4 x minus a to the third. But the final thing I would like to do here is re-express this as a power series. So give me a hand with that. If I want to re-express this as a power series by generalizing the terms, what is this going to look like? So one thing we can kind of plug in right away is that I know I have x minus a to the power of n. But if I look at the individual terms, look at the coefficients, I'm going to have, maybe I should make some more room here. I know that, I'm still going to have c to the n. But look at what else is going on with these c sub n values. I also have 2c sub 2, 3c sub 3, 4c sub 4. I'm also going to have all of these multiplied by n. So n times c sub n. Is that enough? So any questions about how I got this guy here? All right, so that's finding the derivative of a power series. Let's go ahead and find an integral now. So let's go ahead and do the same thing. Let's actually write out the first few terms here. So it's gonna look the same, c sub 0 plus c sub 1 x minus a.
Is it always a good rule of thumb to get to the fourth one?
I'm just stopping it kind of arbitrarily. Really, I'm just trying to fill up the screen. If you need more, you can always put more. If you don't need this many, that's fine. I'm just there is no real reason that I'm going up to that power 4 term. So now what I want to do, I want to come up with an expression for this antiderivative. So what's going to happen to that first term? What's the integral of c sub 0, or the antiderivative of c sub 0?
Like c sub 0 x.
Yep. How about the next one? C sub 1 times x minus a. So think about the way power rule works with probably the first rule of integration you learned. I'm going to increase the power on my variable by 1, and then divide this whole term by whatever that new power is. And the rest of these are going to kind of follow suit. So now that we've done that, let's try to generalize this power series. And really this first term should be so help me build up this power series, or yeah, build up the generalization of it.
X minus a to the n over n. That's what I can think of right now.
X minus a to the n over n. So that definitely fits.
Would it be n plus
Because-
one?
I'm sorry, what was that?
Wouldn't it be n plus one or no?
We can do that. I mean, keep in mind that we haven't really, I mean, all we really know is that these need to be the same, right? Whatever this power on n is, needs to be the same as the denominator. So I think we can actually, we can do this where we, basically we could do it either way. So let's go ahead and fill in this detail. I still want my power series to start with 0. So because of that, you know, I'm still going to have this coefficient. And let's say if I want to build this power series based on that coefficient, then I should probably have this be +1 and +1. Is there anything else we have to worry about? All right, so another way we could have looked at this, and let's just look at it for the integral. It's not, we don't need to look at it for both the integral and the derivative. But remember, when we have a polynomial like this, we can really just integrate term by term. And because of that, let's just integrate the general term that we were given. And keep in mind that when we do this integral, we're really doing it with respect to x. So for now, I'm going to go ahead and pull out the c sub n because that's a constant. So I'm integrating x minus a to the n times dx. So really, I can just apply the power rule there. So this will be equal to c sub n times x minus a to the n plus 1 all over the new power of n plus 1. So not a coincidence that basically both of these methods gave us the same result. And I'm not going to go back to the last slide and do it, but if you take a similar approach with the derivative, you can also get that general term that way. Any questions on what I did there?
Do we still include like plus C?
You can, but the reason I'm not including that here is because basically that would just, you know, keep in mind that we start with a constant here. So really, if I have a new power series, I'm going to have a new constant, and that'll just get absorbed into this definition here. All right, so now let's do some stuff with this. So this is a series I think we looked at last night. Looks pretty terrible. So we could take the approach where I write out the first few terms, take the derivative of all of them, and then try to regeneralize. But can I just take this derivative directly?
No. Oh, wait, you could.
Right. So keep in mind here, I'm trying to find the derivative f prime of x. So when I take that derivative, what's the variable I care about?
X.
It's only x. So let's just start out by doing this. -1 to the n is a constant. I mean, it varies, but it varies with respect to n, and I'm not taking a derivative with respect to n. So really, I get to treat all of these things that don't vary with n. I get to treat them all as constants. So that means I get to pull out the -1 to the n. I get to pull out the 2 to the 2n. I get to pull out n factorial squared. And then from there, I can multiply all those constants times the derivative of x to the 2n. What is the derivative with respect to x of x to the 2n?
Would it be x to the 2n minus 1 over 2n?
Let's think about that. Let me give you a
doing-
parallel. Go ahead, Jacob.
I was doing the antiderivative.
Yeah, you kind of got them mixed up.
So then it'd be 2n x to the 2n minus 1.
There you go. So I'll just I'll throw a parallel example over here to the side. Let's say I have d dx of 7x to the 10th. That's going to be 10 times 7 times x to the 10 minus 1. So any questions about where that derivative came from? And just to kind of restate, hopefully you are recognizing that it's just taking derivatives the way you already know how to do. It's just now you're doing it in the realm of series and sequences, which, because, all the stuff I'm about to box in here, because all the stuff I'm about to box in, or that I did box in, is constant with respect to x, doesn't really affect my derivative. Any questions about that one? All right, let's go ahead and keep on going. So now I have this guy. I want to represent this function as a power series, and I'm going to give you a little hint here. I want to get this by differentiating some other power series. So basically, I will call this capital F of x. Or basically, and the way I'm trying to find that is the derivative of capital F of x is equal to f of x, which is equal to 1 over 1 minus x squared. So can I find a function whose derivative is 1 over 1 minus x squared. Or how do, in general, how do I find a function whose, so let's say I gave you a derivative and I want you to tell me a function that might have that as its derivative. What process am I really asking you to do to 1 over 1 minus x squared?
You want to integrate it?
Yeah, we're going to take the antiderivative, we're going to integrate it. So let's find this thing. Integral of 1 over 1 minus x squared dx. Do a convenient rewrite. So how do I find this? What is this antiderivative? Help me out with that.
It's just -1. It's just 1 by 1 minus x, right?
This is just 1 over 1 minus x plus c. So this capital F of x here is just 1 over 1 minus x. Do I have a power series representation for 1 over 1 minus x?
A a over 1 minus r, right?
Yeah, so we have, I mean, hopefully
Yeah,
from
it's
here
just
we can,
x squared.
it's
It's
just
just
what?
it's just 1 plus x squared plus x cubed.
Right, there you go. So yeah, it's this infinite series here, which, you know, we've kind of seen a few times as the geometric series. So let's do this. Actually, I'll give you a choice here. Do you want to generalize this and then find the derivative? Or do you want to find the derivative of this thing and then try to generalize it? Really does not matter which way we go. So first person who votes, I'm gonna follow suit.
Let's find the general function.
Okay, so let's go ahead and generalize this as a power series, which I believe was just x to the n. And we've done this today. So this is our power series for and I know that if I differentiate this, I'm gonna get what I want, which is 1 over 1 minus x squared. That's what our antiderivative told us. So what is this power series going to look like? So keep in mind here, I can differentiate this directly just by differentiating the general term. So if I differentiate that, that's just, you know, probably the first technique in differentiation you learn. I get n times x to the n minus 1. And because of the theorem I gave you where We know what the radius of convergence is of the power series associated with x to the n. And I know that when I take the derivative, I'm going to have the same radius convergence. So the radius convergence is also 1. So basically, my interval of convergence will be -1 to 1. All right. All right, so now I want to find the power series representation for this thing. So is there a derivative or an antiderivative I can take of some other function? Remember, our only real weapon is this thing. So basically, is there some other function that more closely resembles this geometric series sum, whose derivative or antiderivative will look like the natural log of 1 plus x?
Isn't it the antiderivative? Won't that be
Anti-
1 over 1 plus x?
Right, there you go. So I know that this will give me this this antiderivative. So we should probably first do this. Can I represent 1 over 1 plus x as a power series? Really, another way to ask that is like, can I represent that as a geometric series? So I'll go ahead and fill this in for you, but this geometric series is 1 minus x plus x squared minus x cubed plus x to the 4th. So from there, we'll go ahead and do this one differently we did last time. So now I have this base function that looks like a geometric series. And like we've already shown, I want to find the antiderivative of this. So this antiderivative is going to be x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4th plus 1/5 x to the 5th minus 1/6 x to the 6th, and finally plus 1/7 x to the 7th. So can we generalize that now?
Would it be -1 to the n times x to the n over n?
Okay. Let's test out a few things and make sure that works. So when n equals 0, I'm going to have -1 to the 0, which is 1, x to the 0, which is 1, and n, which is 0. So I think this is a good start. But I think we need to make some adjustments so this doesn't happen. So where do we need to make some modifications?
Could we make it n plus 1?
Which one?
The bottom.
So
Or
we
you'd
make
have to do
that,
it to all of them, right?
if we make that one n plus 1, then this is going to get fixed. So at least now it'll be defined. But my first term should be x. So I need to do this one too. But is the alternation okay? It looks like the alternation is okay because the antiderivative, basically I started off with a sequence or a series where the first term is positive, second term negative, and then it just alternates. The antiderivative did not change that. So I think I can still get away with -1 to the n. But yeah, the other two need to be changed to n plus 1. And for the same reason as before, the radius of convergence is 1. So taking a derivative or antiderivative does not alter the radius of convergence. Any questions here?
Professor, I don't understand why is f of x equals 1/1 plus x?
Because, so remember, this is our goal right here is f of x equals natural log of 1 plus x. But really, right now, the only way we know how to transform a function into a power series is by trying to mimic a geometric series. So I really need to get my function to look like this, basically some constant over 1 minus r.
Okay.
So if we recognize, and someone did recognize that this is the opposite way that it was shown, but these are both true. The derivative of natural log of 1 plus x is just going to be 1/1 plus x. So these two things are equivalent. So natural log of 1 plus x clearly does not, look anything like my geometric infinite sum, but 1/1 plus x really does. With a first term of 1 and a common ratio of -x. So that first term and common ratio was what enabled me to build this up. And then,
Yeah, but then that's not f of x, right?
yeah, I shouldn't be calling it f of x. Yeah, you're totally right. Because this integral, it's f prime of x, right?
Hmm.
So yeah, the integral of f prime of x becomes f of x. So yeah, thanks for catching that. That would have been confusing to post that. Any other questions about this one? All right, let's go ahead and do our last one for the first half of class here. So same thing. Inverse tangent of x is not something I can handle. But does it resemble something I can deal with? Or am I a derivative or an antiderivative away from something I can handle?
1/1 plus x squared.
Okay. So yeah, the derivative of this guy is,
It's oh my god, it's gonna be a how I don't even know how.
so this 1/1 plus x squared, yeah, it's not going to be that difficult because, can I relate this to a geometric sum? To this guy that I keep writing down?
Yeah.
So what are my first term and my common ratio here?
A would be 1 and x or r would be -x squared.
-x squared. Very good.
Oh, what was I thinking? It's ix.
Yeah. I mean, yeah, this one's going to be, yeah, it's not going to be so bad. In fact, 1 over 1 plus x squared, I think, is something we did earlier in this section. So let's do this the opposite way. I know that f prime of x is going to be this series 1 minus x squared plus x to the fourth and so on. So let's generalize this and then we'll take the antiderivative. So I'm going to go ahead and skip forward because we've already done this antiderivative or this series, but this should just be negative 1 to the n times x to the 2n all over nothing. What did I do that for? Yes, just negative 1 to the n times x to the 2n. So if I take an antiderivative, which is what I want to do, let's just take the antiderivative of the general term. So what's that going to look like? So hopefully someone's thinking it, but basically this is just power rule again. Remember that negative 1 to the n, that's all constant as far as we're only integrating with respect to the variable x. So then this other will be x to the 2n plus 1 all over 2n plus 1. And if memory serves, the radius convergence was 1. Because it was for the other example where we dealt with 1 over 1 plus x squared. Any questions here? All right, we're not quite to the halfway point, but let's go ahead and take a break. So we'll do one more section tonight. Let's go ahead and break for now and come back at 7:35. All right, so let's go ahead and do one more section tonight. There's go ahead and start this. So there are 11 sections in this chapter. This is number 10. And the last one is really pretty short, so we'll save it for Tuesday. So let's go ahead and get into this one. So this is all about Taylor and Maclaurin series, which is kind of a build-up, kind of the next follow from what we just did. So, we just did this basically representing functions as power series. But remember that we were really limited on what kinds of things we could do. So let's just say we have a power series that represents this function, some function f of x. So if you think back to think about what our three options are for power series. They either converge for all values of x. That's kind of your best case scenario. They might converge for some values of x inside a finitely large radius, or kind of the most limited cases, they might only converge for a single value of x. But even in that worst case scenario, you get that this power series, and keep in mind, by the way I'm expressing this, this is centered at x equals 0. So because of that, kind of our most limited, our quote unquote worst case scenario is that this series will converge for x equals 0 and absolutely nowhere else. But at least converge for x equals 0. So at x equals 0, the series and the function must completely agree. So what does that mean, completely agree? What that means is my power series is going to have the same value at f of 0. It's going to agree at, so when x equals 0, that power series and my function are going to have the same exact value. But beyond that, they're going to have the same slope. They're going to have the same first derivative. They're also going to have the same second derivative and third derivative, and so on. So when I say they completely agree, not only do they have the same value, but all of the rates of change, first derivative, second derivative, an infinite number of derivatives have to agree. So let's go ahead and write out the first two terms of this power series. And let's use that idea that these functions have to agree. So again, this will be like c sub 0 plus c1x plus c2x plus c3 x squared, c3x cubed, plus c to the 4x to the 4th, plus c to the 5th, or c sub 5x to the 5th, and so on. So keep in mind, these functions, so far, the only kinds of functions we can represent as power series are the ones that we can kind of manipulate and force to look like a geometric series. But now we're going to introduce this technique where I can make any continuous function. I can make any continuous function into a power series. So we're going to go off this idea that this agreement has to happen. So let's start, looking at the specific terms here. If I were to take this power series and just take f of 0, if I put 0 in for x, what am I going to get from this power series? Well, if I put in 0 for x, the only term that's going to survive is c sub 0. So now let's take f prime of x here. And I'm just going to go ahead and stick with, instead of generalizing it, let's just differentiate the first few terms here. The first derivative is going to be c1 plus 2c2x plus 3c3x squared plus 4c4x cubed plus 5c5x to the fourth. So I want to take the first derivative here. If I take the first derivative, the only term that's going to survive by putting x in for 0 in for x is going to be c1. I'm going to need to do that at least 2 more times to kind of illustrate what pattern happens here. So now the second derivative, I'm going to have 2c2 plus 6c3 plus 12c3x plus 12c4x squared plus 20c5x to the third. I really should be putting ellipses here. And if I do f double prime of 0, the only term that's going to be left standing is 2c2. Let's do one more derivative. F triple prime of x, I'm going to have 6c3 plus 24c to the fourth x, or c4x, plus 60 c5x squared, so on. Then if I evaluate that derivative at 0, the only term I'll have left is 6c cubed. So how can I generalize what these derivatives are equal to? So let's say instead of f prime or f double prime or what have you, I'm going to have f, if I take the nth derivative at 0, what is that going to be equal to? So those terms are, c sub 0, c sub 1, 2c sub 2, 6c sub 3. So clearly some part of this is going to be c sub n, because I want that coefficient. The other part that is important is, so what are the coefficients of those c terms? So for the 0th derivative, or just the function itself, that coefficient is 1. For the first derivative, that coefficient is 1. For the second derivative, that coefficient is 2. And for the third derivative, that coefficient is 6. Without really going through it, can I find the fourth derivative of 0? What is that term going to be if I were to go one step further?
It'd be 24.
Yeah, it'd be 24c4, right? Now, can I generalize basically what is multiplied? Basically, what am I multiplying by Cn when I generalize these derivatives?
Would it be n times n plus 1? Or no, that's not right.
So, I mean, you're kind of on the right track, because what you have is, it's n times n plus 1 times n plus 2, but basically, when does that stop? So is there anywhere else you've seen this arrangement where basically you take a number and you multiply it by the integer above it, and then by the integer above that, stopping at something? Yeah, that's factorial. So let's rewrite that. Basically what I'm gonna have here is the nth derivative evaluated at 0 is gonna give me n factorial times c sub n. So hopefully now that we've said that, it makes sense that that's gonna happen indefinitely. If you want this explained, please ask me, but for now, I'm just gonna write down that 0 factorial equals 1. 0 factorial equals 1. 1 factorial equals 1. 2 factorial equals 2. 3 factorial equals 6, and 4 factorial equals 24. So if we were to do this again, we would get 120. And really that pattern continues indefinitely. So hopefully we're okay with this relationship. But what I really want to do, I want to know what I want to solve this for my coefficients. So my coefficients are basically going to come from this. The nth derivative at 0 over n factorial. So if I if I have some function, doesn't matter what the function is, so long as I can differentiate it an infinite number of times, that is how I'm going to evaluate. So these, in the last section, we kind of treated these c sub n as, mysterious, like just a list of coefficients that I didn't really mention or suggest where it came from. This is where it's going to come from. If I wanted to have some function and I want to match match the value of its function and the value of all its derivatives, then that's how I'm going to build these coefficients. By taking the nth derivative at my center point, dividing that derivative by n factorial, that's how I'm going to get any given one of these coefficients. So any questions on how I built that? It might not be clear why I went through all that trouble, but hopefully it will be soon. Any questions now? All right, let's go ahead and keep on building up. So the thing we're going to be doing now is called a Taylor series. And what a Taylor series does is it allows us to approximate any function with a power series or a polynomial. So we were very, very limited in that last section, but now we're going to have a more, more general, more powerful approach to take any function, no matter what it looks like, so long as it's continuous and differentiable with some power series. So here's the way you construct that, and hopefully this looks familiar. The example we just did, kind of the building we just did, we had our center point being 0, but really you can set up a Taylor series where I can approximate a function around any center point, which I'm calling in general A. Some other ideas we're going to talk about. So Taylor series is infinite. So note here that, by definition, a series in mathematics is an infinitely long sum. You're adding an infinite number of terms together. Contrast that with a Taylor polynomial, where basically I build it the same way as I build a Taylor series, but I cut it off. Basically, I take finitely many terms and I call that, basically that's accurate enough, and then I move on. If you see the phrase Maclaurin series, that is a Taylor series, but it's specifically the one where this A value is equal to 0. Any questions about any of these definitions so far? Okay.
I just have this one doubt. Just one doubt. I mean, why is it being? How do I put it? Like, why is it being infinitely? Why is it infinitely differentiable? Like, it's not infinitely, like by n times.
So for this to work, you do need a function that's infinitely differentiable. What I mean by that is I can take the derivative of this function as many times as I want. And even though we don't really do it, you know, the vast majority of functions we've dealt with are infinitely differentiable. If I, thinking back like to all the functions we've looked at, I don't think we've looked at one that isn't that way. One thing I will bring up is this. Let's say you have this function. Let's look at this, f of x equals x squared. What's the first derivative?
2x.
2x. What's the second derivative?
2.
What's the third derivative?
0.
0. What's the fourth derivative?
Would it also be 0?
Yeah, I mean, so even though like it's not interesting to do it, polynomials are infinitely differentiable. It's just after some point, like the 100th derivative is also 0. I mean, this is infinitely differentiable. It's just the derivatives aren't interesting. There's no rate of change after a certain order. Yeah, we're going to be dealing with function.
Yeah, but then the only thing that I have the doubt about is like, if you have that, if you have a function, can you just give an example of a function which could be written down in Taylor form?
A function that could be what? I'm sorry.
Can you can you just write down a function which could be converted, which can be converted into some sort of Taylor series?
Yeah, we'll definitely do that. So we're going to do that right now, actually. So I want to find a Maclaurin series for this. So remember that a Maclaurin series is centered at a equals 0. So let's just make sure that we can do this. Is this function f of x equals e to the x, is this differentiable once? Does the first derivative exist?
Yeah.
Yeah, what is it?
E to the x.
E to the x. And what's the second derivative?
Also e to the x.
Yeah, so this one, there's a reason we're starting off with this one. Basically, every derivative of e to the x is e to the x. So this is actually this is going to be a pretty simple one to build, but it's also a really it's a good one to get started on. So let's go ahead and start building up this Taylor series, which I call capital T of x. So it's going to start off by, we want the function, we want the Taylor series to agree with the function. And so the first most basic level of agreement is they better share the same value at x equals 0. They also better share the same first derivative. And then this is why we went through the trouble to build up these coefficients, because this is how I make the derivatives match, is by structuring this series like this. So now let's start building this. What is f of 0? So hopefully, yeah, it's just one. And really, because of that, I can fill in all of these. F of 0, f prime 0, those are all equal to 1. So this becomes 1 plus x plus 1/2 x squared plus 1/6 x cubed plus 1/24 x to the 4th, and so on. So if I want to figure out what the radius of convergence is, I really need to generalize this. So clearly I have x to the n. Maybe not quite as clearly I have over n factorial. So here's what we have. I know I have a function e to the x, and I now know I have a Taylor series given by x to the n over n factorial that basically approximates e to the x, and it approximates it very well over some radius. But now I need to know what that radius is. So how do I find the radius of convergence?
Isn't it 0?
Sorry, what was that, Rias?
Well, shouldn't it be? I don't know. Is it 0?
Well, I mean, how did you get that?
No, I didn't. I just assumed.
So yeah, it might be, but let's actually go ahead and let's go through the ratio test to come up with a conclusion. But just to reiterate from last night, if you're looking for radius convergence, almost always the way to investigate that is to do the ratio test. I mean, before long, you know, I'm going to suspect that most of you, not most of you, but some of you are kind of there where you can look at a series and maybe understand where it's going to converge, or maybe you at least have an idea. Maybe you even have an idea with this one, but the only way to really justify it and convince me or somebody else is going through the going through these methods to prove your claims. So this ratio test is going to be x to the n plus 1 over n plus 1 factorial over x to the n over n factorial. And if I start canceling stuff out, I'm actually going to, no, I can't drop the absolute value because x might be negative. The x to the n plus 1 is going to cancel out the x to the n and leave just an x left. We'll bring up the n factorial, and I'm going to break up the n plus 1 factorial into n factorial times n plus 1. So that cancels, and I have this, the limit as n approaches infinity of absolute value of x over n plus 1. What is this limit going to be?
It's 1 over.
Take another look.
0?
It's going to be 0 because as n gets very large, that denominator is going to grow unbounded. So basically, this is going to get smaller and smaller and smaller. So you get absolute value of x times 0. Which is equal to 0, which is less than 1 always. So because of that, what is my radius of convergence? Or what value, for what values of x does this series converge?
Only 0.
Only 0?
I'm sorry. 1.
So remember, let's go back to just kind of how ratio test works. Ratio test gives me that a series converges when the ratio is less than 1. So because this limit here ends up being 0, it does not matter how large x is. It will always, basically the limit's always gonna be 0, no matter how large x is allowed to be. As n gets larger, and remember, this limit does not depend on x. This limit only depends on n. No matter how large or small, since I have absolute value there, no matter what x is, this limit given by the ratio test will always be 0. So because of that, this series converges for all real numbers. Any questions on that? So basically what this means is, because this series converges for all real numbers, this function is exactly equal to that Taylor series, because I can make them as close to each other as I want. So I think that it's worth looking at with a graph. So here is, I'll go ahead and dial this back to 0. I have a couple of different things here going on. So this black curve here, this is y equals e to the x. And this f of t, hopefully you recognize this as the Taylor series that the Maclaurin series we just built. So basically what I'm graphing with the red there is, I'm making a Taylor polynomial. So basically I am taking the first so many terms of that series. So if I just take the first term in the series, the only way that my Taylor series is going to agree with my function is at the value of f of 0, at whatever the function value is at x equals 0. But let's say I take 2 terms. If I take 2 terms, so go up to the first derivative, then you can see that this red line here still mimics the function, but now it kind of mimics the slope of the tangent line at that curve as well. So what if I make them agree up to the second derivative? So then if I zoom out, you can see that they get a little closer. But still, as you get away from that center point, they start to deviate quite a bit. And really, if I keep taking terms, the more faithful this gets to the function. So let's go ahead and let's just zoom out and change this to, I don't know, 25. So now that I've done that, I can't actually see any difference. All I see is the curve of the graph of the black line. So actually I had to zoom out quite a bit, and I see now that if I get more than 10 units away, then I'm going to get, if I get more than 10 units away from my center point, then you start to see this deviation. And just to kind of refresh your memory, I have an exponential function here. So as x gets more and more negative, then that black curve is just simply going to, it's gonna more closely approach 0. So let's go a little further and see if I can clean that up more. Let's just double it and go to 50. Ooh, that's weird. Okay, so what's going on with this graphing calculator is it's taking a while because it basically has to calculate my my Taylor series up to 51 terms, and it's going to take a bit.
Bigger.
Mhm.
Do you say goodnight to Daddy? Night.
So I'm going to actually go ahead and bail out on that. It's going to take a little longer than I want.
Professor.
Yep, go ahead.
But if you're sort of like considering it, f of 35 is like a solid value, right?
What's a solid value?
Like if you're taking f of 35, shouldn't that sort of like be a solid value? Like
So keep in mind what my function is defined here. So
okay.
let me go ahead and I'll kind of unpack the way this is working. Basically, the way I've defined this function is basically I'm filling in values of t. So basically what that value of t is doing is that defines how many terms in my series I have. Really, I shouldn't be calling it a series. I should be calling it a partial sum. So let's just kind of back up to, let's just make t equal to 1. Then what that is doing is, all right, I'm letting k equal 0. Then I plug in, x to the 0 over 0 factorial. And then I let k count up to 1. Then I have x over 1. And then I stop there because I've reached my value of t. So really what this function value is doing is basically 35, I'm going up to and including the 35th derivative of e to the x. So basically I'm taking the first 36 terms of the Taylor series. But I'm kind of running into this place now where I know mathematically that since I calculated the radius convergence and found that it was infinite, I know that I can make this Taylor series as close an approximation as I want to e to the x, but I'm running into this situation where I don't have the computing power to do it quickly.
But I'm okay. After the class.
You sure?
Yeah, after the class. Perfect.
Okay. All right, so I'll go ahead and close that down. Back to this. So let's do something a little similar. So now I want to find a Taylor series that's centered away from x equals 0. So that's why I have to be clear about this. A equals 2. So to do a Taylor series, I really have to, basically I got to take a bunch of derivatives. It was really easy with that last example because I already know what all the derivatives look like. So maybe we can run into something similar with this. What is the first derivative of e to the negative x?
Negative e to the negative x.
Yep, negative e to the negative x. How about the second derivative?
E to the negative x.
Right. So hopefully you see that that is going to just alternate back and forth indefinitely. So from there, I can start building up some derivatives. So I got the general derivatives, or I mean, expressions for the derivatives at any x, but now what I need to do is I need to evaluate this function and all of its derivatives at that center point. So this will be e to the negative 2. F prime of 2 will be negative e to the negative 2. F double prime of 2 will be e to the negative 2. And then so on and so forth. They're just going to alternate back and forth. So now that I understand that and see a pattern, I can set up my Taylor series, which is going to be e to the negative 2 plus, no, not plus, minus e to the negative 2 times x minus 2 plus e to the negative 2 over 2 times x minus 2 squared minus e to the negative 2 over 6. Actually, maybe I should be more explicit with all these. And being explicit like this, I think will make it easier for me to generalize. So now that we've done, let's try to generalize. So how can I generalize this based on the first several terms that I've written?
Would it be -1 to the n times e to the -2 times x minus 2 to the n all over n factorial?
Yep, I think that's perfect. So that is a good Taylor series for this situation. Let me just make sure all the signs match up and everything. Yeah, that looks great. So this is a good Taylor series, but now we want to know how good it is. Basically, I want to know what values of x can I trust this for? Like where can I make it be a good approximation? So need the ratio test. So if we look at this limit, I keep leaving out this limit operator. All right, so what cancels out when I evaluate this? I'm going to ignore the alternation. Because e to the -2 has nothing, basically that it has, n does not modify it, so that just cancels out easily. I'm going to go ahead and ignore the alternation because that will just, absolute value will just make that into 1. This power, or basically all I'm going to have left is a single power of x minus 2 in the numerator. So what I have left is x minus 2 times n factorial over n plus 1 factorial, which I am hoping this looks similar to what we just did. So factorials cancel. So again, what is this limit going to become?
0.
Be 0, which is also is always less than 1. So that means my radius of convergence, or let's say it this way, T of x converges for all real x. So again, once I take an infinite number of terms, this Taylor series, this polynomial looking structure will be exactly equal to e to the negative x. Any questions here?
So is it because it's centered around 2 that you've put x minus 2?
Yes.
Okay.
So basically, we got an infinite radius of convergence here. Let's say we got a radius convergence of 0. So basically, the only place where this series would converge, the only x value, would be the center value. For a lot of the things we've looked at, especially the last example, that center value was x equals 0. But if this series in particular we're going to converge at only one place, it could not be x equals 0, because that would make this bracket right here. X equals 0 would make x minus 2 to the n not equal 0. Which, I mean, when you get into that worst case scenario that I keep calling it, where your series only converges for one value of x, really you have a series that the only way it can converge is if all but one of the terms are 0. Which that can't happen if I have my center value be anything other than whatever a is. And the last, I feel like I'm harping on this a little bit. It's an important question and an important thing to really emphasize. But think back to a theorem from a couple of sections ago. If you have a power series converges in one of 3 ways. Either it converges everywhere, which our last 2 examples did, or it converges for some finite radius, or it converges at the center point. Actually, I'll go back one. If it has a finite radius convergence, let's say your radius convergence is 4, then it converges basically 4 units above whatever that center is and 4 units below. Has to be centered around whatever the center point is. And finally, your last scenario is if the radius convergence is 0, and in that case, it's only going to converge at a equals 2. All right, so let's do this one. I found the Maclaurin series for this guy. So I've done a couple of these now, so I'll go ahead and let you drive. How should I start working on this?
Can you look at the derivatives?
Let's look at the derivatives. What is the first derivative?
Isn't it cosine x?
Cosine x. All right, moving on. What is the second derivative?
Isn't it negative sine x?
Negative sine of x. All right, let's go again.
Negative cosine x.
You have cosine. Fourth derivative.
Sine x.
Sine of x. So hopefully that's far enough to show you that this will be cyclic. Basically, the next 4 derivatives are going to be the same as those ones. So from here we can start. I think we can start, or we can continue. So forgot I was gonna let you tell me how to proceed through this. So what should I do next?
Make the Taylor series.
Okay, how should we do that?
It'll be like sine 0 plus cosine 0.
Yeah,
minus
okay.
Sine 0.
So, and yeah, it was so something we kind of glossed over. Maybe you all just realized this, but this name Maclaurin means that my center point is by definition 0. So f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial x cubed, and we will continue from there. F of 0, what is sine of 0 equal to?
Zero.
0. F prime of 0, so what's cosine of 0?
Isn't it 1?
That's 1, so this one becomes 1x. F double prime of 0 is going to give us negative sine. We already know those are. So basically what I've already picked up on is that all of my odd number terms are going to be zeros. All of my even number terms, so, or I guess maybe I shouldn't generalize yet, but f triple prime, so negative cosine of 0 will be -1, so this will be -1 over 3 factorial times x cubed. And then the next one's gonna be 0x to the 4th. But here's the thing, we've only really picked up a couple of terms that we can even talk about. Really, we need to generalize this based on the non-zero terms. So far it's just these two. What is my next term going to be? So if I were to concern myself with the 5th derivative, or sorry, the 4th derivative? No, 4th derivative's here. So what would the 5th derivative give me?
Would it be -1 over 5 factorial x to the 5th?
-1 over 5 factorial x to the 5th. I think I have one concern here. What would the 5th derivative be?
That would be positive, right?
It'd be
Because
positive.
cosine x.
Yep. So because of that, this is actually going to be positive. So now I have 3 terms. Do I have enough to generalize this Taylor series, or should I get another non-zero term or 2? Let's get at least one more. Next one's going to be 0x to the 6th. And then -1 over 7 factorial x to the 7th. So hopefully that's enough. Can we start generalizing this Taylor series? Hopefully we see the alternation. But what might be tricky about this is the fact that, all right, I know I have X and I know I have increasing powers, but they're not increasing in a way that really makes this easy to look at. The powers are going from 1 to 3 to 5 to 7. So how do I relate that to this index, which starts with 0? So basically what I want is this. Let's make a table. Actually, let's put it down here. So n equals 0, 1, 2, 3. When n equals 0, my power on x is going to be 1. When n equals 1, my power on x is going to be 3. How far do we go? Oh, we went the first 4. So this is perfect. So when n equals 2, I want my power to be 5. And when n equals 3, I want my power to be 7. So is there a way to relate my power on x to the index of my series? And since we're going to need to do this one as well, we're going to have to generalize this factorial as well. So when n equals 0, this will be 1. When n equals 1, this will be 3. Oh, this will be, so basically if I can figure out the relationship for 1, I can get them both. So can I express my power on x? Maybe to help you here, even though we didn't go this far, do I know what these boxed values are going to be when n equals 4 and n equals 5?
Nine and 11.
9 and 11, how did you get those?
They're increasing by 2.
Okay, so I'm always increasing by 2. So what kind of relationship is this where basically my input n increases by 1 and my output increases by 2? So that constant change there, that constant additive change, what kind of relationship am I looking at there?
Is it like 2n plus 1?
Yeah, that's exactly it. So I mean, what I was getting at is this is a linear relationship. So x to the 2n plus 1, and then over 2n plus 1 factorial. So that is my Maclaurin series for sine of x. Any questions about how we arrived at those values? Because generalizing these is going to be one of the things we have to deal with. All right, so I've got the Taylor series or the Maclaurin series. How do I find the radius of convergence?
The ratio test.
There you go. So let's go ahead and go through the ratio test and see where this Maclaurin series is actually a good approximation. If it's okay with you, I'm going to ignore the alternating term because I know that's just going to get washed out by the absolute value. So then I'll have x to the 2 times n plus 1 over 2 to the 2 times n plus 1 factorial all over x to the 2n plus 1. And I'm wondering if any of you are suspecting kind of how this is going to go based on what we've noticed about how factorials affect these this ratio test. So I'm gonna go ahead and pull out an x squared, and then I'll rewrite these factorials so I can actually manipulate them.
So it's 0.
What is 0?
The value, the final value is 0.
Yeah, so this limit ends up being 0, which is less than 1. So we got another Taylor series that converges for all real numbers. And that won't always necessarily be true, but so far, these 3 examples, it has been. So this one was a little more difficult because generalizing this Taylor series required a kind of an extra wrinkle there. But anyway, anybody have any questions about the way we did this? All right, let's move on. So I want to find this Maclaurin series now. So I'll go ahead and fill in the derivatives because a lot of this is going to be very familiar. Okay, so from there, let's go ahead and start building up this Taylor series. Really a Maclaurin series, but we just know it's centered around 0. So now we have that f of 0 is 1. And just like last time, all of these sine terms are going to come out to be 0. I forgot this, didn't I? All right, so now that after doing sine now, is it a little more clear how this one generalizes? So hopefully we see the alternation. We still have x raised to some power, and we still have something factorial. So let's go ahead and distill this down to its first few non-zero terms. 1 minus 1/2 x squared plus 1 over 24 x to the 4th. So what should I raise x to generalize this Taylor series?
Power of 2n.
2n. And just like last time, that's going to be true for the factorials as well. So here's my Maclaurin series for cosine. And I'll go ahead and leave it if you kind of want to practice this, but as an exercise, you can see that converges, I'll just say converges everywhere. So for all real values of x, you'll get this convergence. But I'll when we've done a few of these, I'll go ahead and leave that for you to, if you feel like you need to practice. I encourage you to check that result as well. Make sure that you can come up with that. Any questions for this example? All right, I'm going to go ahead and skip by this one. But again, I mean, you can definitely go back and go through this. I'm going to post these slides as soon as I get done tonight. So if you want to go through and practice with this one, yeah, I would encourage you to do so. So let's do something a little more in general. So I want to find a Maclaurin series for this thing. 1 plus x raised to the power of k. And k is any real number. So I want to build a Maclaurin series, so how should I get started?
Find the derivatives.
Okay. So what's the first derivative of this thing?
K times 1 plus x k minus 1 raised to k minus 1.
Raised to k minus 1. Good. What is the second derivative?
K plus 1. No, sorry. K times k minus 1. 1 plus x k minus 2 raised to k minus 2.
Yep. And I'll go ahead and take over from there. We can generalize this a little more. K times k minus 1 times k minus 2 times 1 plus x to the k minus 3. So hopefully we can kind of see how this is going to behave from here. So let's now build a Taylor or build a Maclaurin series for this. First thing, actually, let's go ahead and put in these details. F of 0 plus f prime of 0 times x plus f prime double prime of 0 over 2 times x squared plus f triple prime of 0 over 3 factorial x cubed, and so on. So if I build this up this way, f of 0 is just going to be 1. F prime of 0 is going to be, or yeah, f prime of 0 is, so I have my first derivative. If I plug in 0 there, I'm going to get k then plus k times, oh, I left something off, didn't I? Yeah, kx, that's right. Then k times k minus 1 over 2 times x squared plus k times k minus 1 times k minus 2 all over 3 factorial times x cubed, and I'll go ahead and do one more, k times k minus 1 times k minus 2 times k minus 3 all over 4 factorial times x to the 4th. So this right here, this kind of structure, I mean, this is general. I mean, k can be any real number here. This is called the binomial series. And the reason we kind of call it out as something special is because if you can make your function fit this form, then basically you kind of have a shortcut. You kind of have a template that you can use to approximate it using this this polynomial construction. So let's just really call it out here. F of x is equal to 1 plus x raised to the k, which is equal to this infinite series, 1 plus kx plus k times k minus 1 over 2 x squared plus k times k minus 1 . Any questions there? So now that we have this, let's take a couple of examples and apply it. So, and hopefully this reminds you a little bit of the way we manipulated geometric series. So I'll do one rewrite here. And keep in mind that what we're trying to get to is this. F of x is equal to 1 plus x raised to the power of k, where k is just, k can be any real number. So if we can get this into something resembling that form, then we can kind of use that binomial series and let that take over. So the first rewrite I'm going to do here is this. F of x is equal to 4 minus x raised to the power of -1/2. But something to focus on is I need this first term in the binomial. The first term of the binomial has to be 1. So something I need to do here is I need to factor something out of this. So that first term is a 1. So I'm going to factor out a 4. So that becomes 4 times 1 minus 1/4 x to the -1/2. But when I factored out that 4, I didn't really factor out a 4. I factored out 4 to the -1/2. So let's go ahead and do one more. We'll simplify. This becomes 4 to the -1/2 is the same as 1 over the square root of 4. So this is 1/2 times 1 minus 1/4 x to the -1/2. So from there, now we have this 1 minus 1/4 x. We have this in the form we wanted it to be in. So let's do this now. We can apply that binomial series. I'm going to go ahead and carry the 1/2 just that I'm gonna, when I'm done, I'm gonna multiply by everything. But the way this binomial series, if, you know, when it can, I'll go ahead and fill in the details here, but our first term is 1. Then the next term, I think we said, was kx. So in this, I'll go ahead and actually just write kx. Then plus k times k minus 1. Actually, we need over 2. K times k minus 1 all over 2 factorial x squared. Plus, we'll do one more. So basically, we're trying to fit this form. For our purposes, k was equal to -1/2. But keep in mind, what did we, you know, when we factored this, what became of x? We actually want to replace this with -1/4 x. So first term 1, second term is going to be this product that we're going to have to simplify. So let's get 2 more terms. Hopefully that will help us generalize everything. K is -1/2. K minus 1 is -3/2. All over 2 factorial times -1/4 x squared. And then finally, -1/2 times -3/2 times -5/2 all over 3 factorial times -1/4 x cubed. And before I get into simplifying, let me go ahead and stop there for a couple of reasons. If you have any questions about basically how I've gotten here so far, and really, please double check me. I want to make sure I didn't leave anything out or flip a sign or something. I think it's okay, but yeah, definitely let me know if you see anything that looks out of place, or if you have any questions. Okay, so now let's simplify a little bit. This would be 3/4 over 2, so that's 3/8. Times 1/16 x squared.
Would it be by time? Oh, never mind, because it's squared, so negative goes away. Never mind.
Yeah, okay. Thank you, though. This next one, though, will be negative. Actually, maybe it's going to wash out and be positive. So -1/64 x cubed. And this might not generalize easily, but let's at least take a look after we simplify. 8 times 16 is, I believe, 128. 48 times 64, I have no idea. Right, I think that is all correct. But now, can we generalize this thing? So I am not seeing an obvious way to generalize that. But because this is binomial series, here's something we know for sure. And because we're short on time, I'm not going to prove this. We can another time if you're really interested, but what I'll give you here is that the binomial series, the radius of convergence comes from this. I want the absolute value of x to be less than 1. So for this, let's look at, what our x was. So basically, I'm looking at this. I want the absolute value of 1/4 times x to be less than 1. Or if I re-express that, I'll have -1 is less than 1/4 x, which is less than 1. Or -4 is less than x, which is less than 4. So in this case, my interval of convergence is, or it contains this, -4 less than x, which is less than 4. If you're able to generalize this series, then you can investigate each of the endpoints, but for right now, all I really want is the radius. So kind of a lot of things going on there with that binomial series, but wanted to show you at least one example. Any questions on how that works? Or on anything we did for that example? All right, let's go ahead and move on. Got 2 more examples we can go through. I think we can get both. So, key phrase here is I want to find the first 3 non-zero terms in the Maclaurin series. So I think we're going to have to take a few derivatives. But let's just take only as many as we need. So what's f of 0 going to be? Is f of 0 going to give us a non-zero term? What do you think?
No, because sine of 0 is 0.
Right. So now we know we got to take at least 3 derivatives. So what is the first derivative of e to the x sine of x?
Would it be 1?
Oh, did you already take the derivative? Let me catch up
Oh.
with you.
Sorry.
So e to the x sine of x plus e to the x cosine of x. And then yes, I agree. F prime of 0 would be 1. All right, so now I know I at least need to take a second derivative. So I already know that the derivative of e to the x sine of x is e to the x sine of x plus e to the x cosine of x. But now I need the derivative of e to the x cosine of x. So that'll be e to the x cosine of x minus e to the x sine of x. So am I going to get a non-zero term from all of that? Looks like that is going to be 2. And the third derivative hopefully doesn't get too out of control. Oh, actually, this is nice. So let's go ahead and rewrite the second derivative so it'll come out to a form where I can use it. 2 e to the x cosine x. So f triple prime of x is 2 e to the x cosine x minus 2 e to the x sine of x. So then that gives me another term of 2. Are we okay with that? I feel suspicious of it. I think it looks okay. So I think that's as many derivatives I need to take because I'm going to have 3 non-zero terms. So what are those terms going to be? Let's go ahead and finish them because those 3 terms are going to involve those values of 1, 2, and 2, but it's not going to be exactly equal to that. So tell me how to finish this thing up. So we know that first term was just 0. Second term is going to be x, or first non-zero term. Then 2 over 2 factorial times x squared plus 2 over 3 factorial times x cubed. So first 3 terms are going to be x plus x squared plus 2 over 6, which is 1/3 x cubed. Any questions there?
No, sir.
Yep. No, sir? Okay. We're a little past 9, so let's go ahead and wrap it up there. Just a reminder, there is homework due Tuesday at 5. I'm going to post the quiz and these slides and the video all tonight. So keep an eye out for those. Quiz is due at 5 tomorrow. And of course, next test is going to be on Wednesday evening. So yeah, if you have any questions about anything, let me know. Send me an email. I'll be checking that this weekend.
Wait, Professor, like last time it was on Tuesday.
Last time what?
Last time the exam was on Tuesday.
Yeah, that's correct. This time it's
Oh.
Wednesday.
Okay, maybe something to do with the month.
That's
Okay.
just mean, those are just the days I happen to pick. So yeah, first exam is going to be on a Tuesday, the next one's going to be on a Wednesday, and then the final is going to be on a Thursday. Yeah, I mean that there's no real. Those are just the days that I chose based on where I thought that I'd be done with the sections I wanted to be done with.
It's very interesting. For Professor, can you explain the Taylor, like why you expanded the way you're doing it, like a little bit, as to how you arrive at that?
You mean this example here?
No, not this one. In general, like I'm just trying to understand that.
Yeah, so let me go back. And I'll kind of just reiterate what I did for this first slide here.
Mm.
So basically what I want to do is I want to build a, if I have a power series that represents some function, some infinitely differentiable function, I know that in general, a power series is just going to be built like this, where I have some infinitely long list of coefficients, these c sub n, multiplied by x to a power that increments by 1 with each term. So I want to build a power series that agrees with a function. So I want to agree with the function and the and all of its derivatives, all of them. So that's why I took these first few values here. So here's my power series. If I let x equal 0, so, and really I'll put f of x on the left over here too. If I let x equal 0, then all but one of these terms are going to be annihilated. So that means that f of 0 has to be equal to c sub 0. So basically what I'm doing here, I am coming up with a way to choose systematically what all those all these c coefficients are. So the way I chose c sub or fc sub 0, I'm just gonna have c sub 0 agree with the function when x equals 0. So now let me repeat that process with the first derivative. If I take the first derivative and then plug in 0 for all the x values, then all the terms are going to vanish except for c sub 1. So the way I'm going to choose what c sub 1 is equal to, I just wanted to agree with the first derivative of the function when x equals 0. Repeat that process again. This is where it gets a little bit, counterintuitive maybe, because the way I'm going to choose c sub 2 is I want it to be equal to the second derivative at x equals 0 divided by 2. And then the third derivative, or the next value, c sub 3, I want that to be equal to the third derivative of 0 divided by 6. And finally, I wanted c sub 4 to be equal to the fourth derivative as 0 divided by 24. So basically, if I recognize this pattern, this is how I'm going to choose all my coefficients. And by choosing all those coefficients in this way, I'm going to make sure that, for any function that I can find all these derivatives for, that this power series will agree with my function at that point, and it will agree with all the derivatives at that point. So that's basically how, that's kind of the new ingredient to, a power series is a really generic thing. the way you make a Taylor series for any given function is to choose the coefficients, this C sub n sequence in this specific way.
It makes sense, like, you know, but then then so any given function is infinitely differentiable.
Not necessarily. But it's common enough that like I actually can't come up with an example right now of a function that's derivative that can only be differentiated a finite number of times. So you have to be dealing with a function that's infinitely differentiable to do this.
Like you can't do it for a circle or something, right?
Let's think about that. So let me share a